Alright, so in this video we'll be going into details of how to calculate the net radiation at a surface using view factors, and we'll also be looking at thermal resistances and how to calculate the net radiation and total resistances for this scenario. So let's say we have an enclosed surface or an enclosure with different surfaces. These surfaces are opaque, so our transmissivity is 0, and we've assumed that all surfaces are gray and diffuse surfaces. That means your absorptivity will be equal to emissivity, and diffuse surfaces means that you will have surface emitting radiation equally in all directions and through all wavelengths. Okay, so uh, what happens on surface I? So let's take the image B. Your surface I will emit some radiation Qi. So let's take a control volume just above the surface. The surface will be exposed to an irradiation Gi. So the net heat coming into the surface will be Gi into times the area of this controlled volume, and the radiosity will be Ji times Ai, and Qi will be the net radiation. Uh, will be the net radiation. So if we just look, so another way of representing B is, instead of showing radiosities, we can show uh, the radiosity in terms of what is emitted by the surface. So the emission by the surface due to its temperature, then whatever is irradiated, a portion of it will be reflected. So we have a reflectivity times G times area, and a portion of it will be absorbed. Nothing will be transmitted because the surface is opaque, and we can represent this as a potential which is EBI, that is what is emitted, and radiosity Ji, and you will understand this in just a moment about the thermal resistance. So we can write our Qi from looking at figure B right here, as Qi is whatever the net radiation at the surface will be whatever leaves the surface, that is Ai times Gi, minus whatever falls on the surface, that is Ai into Gi. This can be written as, taking areas common, it can be written as Ai times Gi into Gi, and let's say this is equation 1. So our radiosity is nothing but the summation of whatever is emitted, which is Ei, plus whatever is reflected, that's the reflectivity into Gi. So let's say this is equation 2. So we'll substitute this equation into equation 1, and we get Qi equals to Ai times, we've written Ei plus rho I Gi instead of the radiosity, minus Gi, and if we take Gi in common, or if we take Gi as common, we can write this equation as Ei plus Gi times rho I minus 1. Now whenever you see uh, something like this, remember to use the summation formula for transmissivity, absorptivity, and reflectivity. We'll do that. So the summation of all these three terms is 1, and because our object is opaque, our transmissivity is 0, so our rho I minus 1 will be equal to, this should be minus, so it should be equal to minus alpha I, and we'll substitute that right here. So the net radiation will be equal to Ai times Ei, that's the emissivity or the emission out of the surface, minus the absorptivity of the surface times the irradiance that falls onto the surface I. So because the surface is gray, we can use alpha equals to epsilon I, and our emission is nothing but your emissivity times the uh, emissive power of the body, which is nothing but sigma times T to the power 4. So let's substitute that in the radiosity equation, that's equation 2. We get Ji equals to Ei times Ebi, that's this term right here, plus 1 minus epsilon. That's because your transmissivity can be written as 1 minus alpha, and because alpha is equal to epsilon, I have written it as 1 minus epsilon times G. So we can write Gi, or the irradiance, as radiosity minus Ei, that's the emissivity times the emission power of the body, upon 1 minus epsilon I. Okay, so let's substitute this in our original equation, equation 1. So we'll substitute the value of Gi here, and the equation that we get is our Ai times Ji remains constant, and we just substituted this value instead of Gi. And after taking a few things, in common and doing the math, this is the equation that we get. So if you see, our Gi's here will get cancelled out, and the equation that we'll get will be uh, something like this. It will be Ai times minus epsilon Ji plus epsilon I into Ebi divided by 1 minus epsilon, or we can write this as Qi, or that's the net radiation at surface I, equals to Ebi minus Ji divided by 1 minus epsilon upon epsilon times A. So if you see, this is analogous to what we had for thermal resistances. We had temperature difference as the driving potential. So instead of temperature difference, we have Ebi and Ji as the driving potentials, and that's why we have shown Ebi and Ji in our circuit, or in our resistance diagram here. And the and whatever's in the denominator is our resistance, and that's why our resistance here is 1 minus epsilon upon epsilon A. Okay, so our Ebi minus Ji is nothing but the driving force, and the denominator is nothing but the surface radiative resistance. Okay, so remember, it's the surface radiative resistance, not the thermal. So it's a bit different from thermal resistance, and we have two types of resistance here as well. So this is the first type. This is the surface radiative resistance. So if we have a black body, our epsilon will be 1. So our resistance will go to 0. That means that there will be no resistance offered if you have a black body, no surface radiative resistance that will be offered if you have a black body. But if you have a very large surface, that means if your Ai goes to infinity, that means your denominator will be extremely large, and this entire quantity will be close to 0. So what this means? This means that if a surface is very large relative to other surfaces, it can be treated as if it were a black body. Okay, so you can treat a surface as a black body if it is actually a black body and your emissivity is 1, or if your area is extremely large. Okay, so moving on, we just looked at the net radiation from a surface. Now we need to look at what will be the radiation exchange between the different surfaces of the wall of this enclosure. Okay, so let's look at that. So the irradiance on surface I, so let's say this is the surface I, will be the summation of uh, whatever is emitted by all the surfaces. So Ji is what is emitted from all the different surfaces times the view factor. So whatever is emitted, so whatever is, so let's say this is surface 3. So Ji will be what is radiated out, or the radiosity of surface 3, but a view factor 31 comma J3 will be what will be intercepted by surface 1 right here. And if you want the heat transfer rate, you'll have to multiply by an area, and that's why you have an area here. Okay, so that's why, and we can write this thing for surface 4, 5, 6, 7, and n number of surfaces. So whatever falls onto the surfaces on surface I is nothing but the summation of radiation that leaves all the other surfaces in the enclosure times the view factor. Okay, so our Qi in this term can be written as the summation of whatever is emitted by surface I minus whatever falls onto surface I. So that is the net radiation that is exchanged between the two surfaces, or that is the net radiation from surface I, not exchange, it is the net radiation from surface I. Okay, so let me repeat what this equation means. This equation means, so this equation has an AI Fij times Ji, that the first term is nothing but whatever leaves the surface minus AI times Fij times Ji, which is nothing but whatever radiation falls onto the surface and that is emitted by all the other surfaces in the enclosure. Okay, so this is nothing but the summation of heat exchange between each pair of surfaces. So this will be a summation of heat exchange between 1 and 2, 1 and 3, 1 and 4, 1 and 5, and so on. So I can write this equation as summation of Ji minus Jj divided by 1 upon Ai into Fij. So I just took this term into the denominator and wrote it as 1 divided by Ai into Fij. That's what the raised to the power negative 1 means. And now the driving potential here is Ji minus Jj, and 1 divided by Ai into Fij is called as the space or geometric resistance. Okay, so in the previous slide we looked at surface radiative resistance, and this is another type of resistance which is caused due to the view factor between the two surfaces, and it's called the surface or geometric resistance. So now if you remember, the equation for Qi that we had got in the previous slide was Ebi minus Gi divided by 1 minus epsilon I upon epsilon I Ai. So this is what we had calculated for heat at the surface, and this is the Qi that we got here. So these are the same Qi's and we can equate them. So our left hand side is the potential difference, or driving potential due to radiosities divided by the resistance due to shape factor equals to the potential due to emissivity and radiosity divided by the resistance due to radiation. Okay, this is the radiation resistance due to surface radiation. Now, so ultimately our QI, or the net radiation that we got due to view factor, was summation of j's from 1 to n is the number of surfaces in the enclosure, um, ji minus jj, radiation leaving the surface minus radiation falling onto the surface due to other surfaces, divided by the resistance due to shape factor. So this equation here can be represented in a radiation network approach, in a radiation network where you have two resistances now. One is due to the surface radiation and others are due to the shape factor. So your EBI is what is emitted due to the temperature of the surface. Then you have the radiosity, and a resistance between that is the resistance due to the surface, the radiative resistance due to the surface. Now after we have Ji, you will have heat exchange between different surfaces. So that, and the resistance between the two surfaces will be the resistance offered due to the shape factor. Okay, so this is how you'll represent uh, a nodal network in terms of view factors and emissivities. Okay, so just to understand this, we'll take a simple example, and we'll define, before that we'll define our the two types of resistances. So the first resistance is due to view factor, and it's 1 divided by AI into Fij, and the second one is due to radiation, and it's 1 minus epsilon by epsilon A. So let's take a simple example where you have a surface, where you have an enclosure where surface 1 is sort of a straight line and surface 2 is an arbitrary surface, and we want to find what is the heat being, what is the heat exchange or heat flowing from 1 to 2. Okay, so the first thing we'll do is we'll make a network, we'll make a circuit diagram for this. So EB1 is what is emitted by surface 1, EB2 is what is emitted by surface 2. Okay, so J1 is the radiosity of surface 1 and J2 is the radiosity of surface 2. So the resistance between EB1 and J1 will be RT rad 1. The resistance between J1 and J2, because we just have two surfaces here, we will just have resistance due to one view factor, so we just have one resistance here, and we will have another resistance between J2 and EB2, and that's RT rad 2. Now our resistance due to V factor 1 will be A1, 1 upon A1 times F1, F of 1 2, and resistance due to radiation for 1 will be 1 minus epsilon 1 divided by epsilon 1 into A1, and for 2, surface 2, it will be 1 minus epsilon 2 divided by epsilon 2 A2. So our total resistance, now that we've drawn our circuit diagram, we see that all the three resistances are in series. So in this case, our total resistance will not be nothing but the addition of these three resistances. So that's what I've done here. I've added the three resistances, and our Q12 will be the potential, the total potential difference at the two extreme points. So the total potential difference is EB1 minus EB2 divided by the total resistance. So the total resistance here is the summation of all these three resistances, and I'll write this down as EB1 is nothing but sigma times T1 to the power 4 minus EB2 is nothing but sigma times T2 to the power 4 divided by the summation of the three resistances that we have. So this is the equation that we get for a simple two surface enclosure, and that's how you approach these problems. We'll be doing a problem, I'll be doing another example problem to show you the importance or how to solve some complex uh, radiation networks as well.